So in a manner very similar to figuring out the symmetries and the loudness of overtones, we can do something very similar for combinations. And so in combinations, you're just adding or subtracting two different modes together. And so in order to do this, there's a very similar integral. Now we have the ground state of both modes, okay? And then the final states of both modes, kind of sandwiching again, the transition moment operator, and this is integrals across tau, which is all symmetry space, right? And so, you could get kind of complicated here. You could start talking about combining an overtone with two overtones together, or an overtone with a normal mode, but it turns out the intensity of those sorts of more complicated combinations is typically so low we don't have to worry about them. So really what we're worried about is just so-called fundamental combinations, which is what is embodied by this integral. That is just combining two different normal modes together. Okay, we can be additive or subtractive. So let's walk through some examples, or all the examples for methane. So we start out again with our normal modes that we calculated before. A1 plus E plus 2T2. We have 4 different symmetries here. So we just start with all the different permutations. So we have A1 plus E or A1 minus E. And so how is this going to work? Well, the initial states for both modes, those always have symmetry that are totally symmetric, just like before. So these essentially we can get rid of. These are always going to be A1s, because timesing anything by A1 doesn't do anything, right? And so at this point, we have basically T2 times A1 times E. Well, there's another A1 in there. Oh, where did the T2 come from? Let's back up. That came from mu, right? Mu is the transition dipole moment operator for TD symmetry. It's always XYZ, and in TD symmetry, T2 is what transforms as X, Y, and Z. So then you're left with basically, because you have an A1 here times E, that came from actually what you're evaluating, the two modes that you're trying to add or subtract together. You're left with just T2 times E, because this A1 can go away. So T2 times E, I don't know what that is off the top of my head, but it doesn't matter, because I know it's not something times itself. And if it's not something times itself, it doesn't have any A1 in it. That comes again from the product table. Go back to chapter 2, last lecture, if you're worried about that. Okay, so that tells us that the A1 plus the E or minus the E combination has 0 probability of happening. Symmetry forbidden. Let's go on to A1 plus or minus T2. That is a combination that we could do. And there's actually 2 different versions of this, right? Because we have 2 T2s. One was a bend, one was stretched. Those have different energies. So we're talking about 4 different things here, because each of those 2 T2s also has a plus and a minus, right? All right, so we have our A1 and our A1 starting off from up here. Those we can get rid of. Then we have T2, that's our mu, our transition moment operator. Then we have actually what we're evaluating here, A1 and T2. And so A1 times anything is just itself, so that gets rid of it. So we have T2 times T2. Again, I don't know what T2 times T2 is off the top of my head. I could calculate it if I want to, but that's just a waste of time, because I know T2 something times itself always contains the A1. And if we contain an A1, then by our integral rules and all that we've learned about odd and even integrals, this integral here is going to be non-zero. So these are going to be IR active. Okay, so all 4 of them, A1 plus the first T2 energy, A1 minus the first T2 energy, and then A1 plus the second T2 energy, because there's 2 of them, and then A1 minus the second T2 energy. E plus or minus T2. All right, well again, A1s, those cancel out. We have T2, that's mu, and then we have E and T2. That was what we're evaluating. And so we're going to have to evaluate something here. We could do T2 times T2. We could evaluate that. It is commutative. Or we could, what I did is I evaluated E times T2. And so I had to do some math here. And again, look at the previous videos on reducible representations and product tables of how to get E times T2 being equal to T1 plus T2. So E times T2 is equal to T1 plus T2. At this point, now you have T2 times the sum of T1 plus T2. And so T2 times T1, that's not going to have an A1 because it's not multiplying something by the same thing. But T2 times T2 will have an A1 in it. And because of that, the integral will be non-zero, so this is active. T2 minus plus or minus T2. Why can we do this one? Because, well, there's two T2s, right? So they could couple with one another and make a combination that way. Again, we got the A1s in the beginning. Those can go away. We have a T2 as mu, and then we have T2 and T2. So it's T2 cubed, T2 times T2. We've gone over this before, but equals this, A1 plus E plus T1 plus T2. Because there's a T2 here, that means you're gonna have a T2 times a T2, okay? And so whatever that is, that's gonna have an A1 in it. And so that's gonna be active. So you can see, this is why infrared spectra are really hard in general to interpret, because there's a lot that can go on. A lot of different combinations, right? Some overtones in addition to normal modes. So that's why we'll almost always have more peaks in an infrared spectrum than just the normal modes, just the IR active normal modes, which suggest, right? Remember, there are only two IR active normal modes here, just the two T2s. But yet we have three different sets here of combinations that are IR active that involve symmetries outside of T2.